In this video, we get to talk about how do I take derivatives if my base isn't e? Because up to this point, all the derivatives we've been doing are base e, right? E to some power. Or log base e, right? Natural log. What's my derivative? Natural log of something. So today in this video, we're going to focus on, well, how do I take the derivative if my base isn't e? Now, it's interesting because I actually spoiled this in 3.1. We talked about how to find the derivatives we talked about what the formula would be for a derivative of a to the x. And same thing with log base a. We talked about the formulas for each of those. So today is more just a practice. We're going to practice actually using these derivative formulas. So just as a reminder, if f of x is equal to a to the x, then my derivative, then my derivative is a to the x times natural log of a. It's similar to e to the x because the derivative of a to the x is still a to the x, but you have to multiply it by this extra constant, natural log of a. Natural log of a is just a constant because your base a is a constant. Okay, and then with the logarithm functions, if we'll call this one g of x, if g of x is log base a of x, then your derivative, g prime of x, you're still going to have 1 over x, but you're going to multiply that x by natural log of a. Okay, so you have 1 over x times the natural log of a. So that's just a quick little reminder of these formulas. And now we're going to get some practice actually using these. Okay, so let's look at my first example. Let's look at this. Y equals 11 raised to the x fifth plus 2 power. Okay, we're starting with something that requires chain rule. Okay, because here I have a function x to the fifth plus 2 inside of this exponential function. Okay, so I'll use chain rule to actually calculate this. I'll take the derivative of my outside function, which according to my new formula is just 11u times natural log of 11. Remember, natural log of 11 is just a constant. You can plug that into a calculator. And then I'm going to multiply this by the derivative of my inside function, which of course is just 5x to the fourth. Okay, so there's my two different pieces for the chain rule. And of course, to finish this up, I want to put this all back in terms of x. And so I get natural log of 11. I'll put the constant out in front, times 11 raised to x to the fifth plus 2 power times 5x to the fourth. And there's my derivative. Okay, let's try a little bit more complicated of an example. Okay, if this one wasn't complicated enough for you, let's try a more complicated example. So, y equals 2 to the 5x cubed minus 1. Well, that's going to use one of my new formulas times log of 3x plus 4. Interesting, I didn't specify a base. Well, remember, if I don't specify a base, it's log base 10, right? That's shorthand for log base 10 because that's a very common logarithm that we use a lot. So this is just log base 10. Okay, well, what is this derivative going to need? This is going to need chain rule. Or not chain rule. It is going to use chain rule, but it's also going to use product rule, and I have to use product rule first. So my front function is 2 to the 5x cubed minus 1. And my back function is log base 10 of 3x plus 4. I need the derivatives of both of these. And both of these derivatives end up using chain rule. Okay, so let's start with this one. Let's start with my first function. This one's going to look really similar to the one that we just did. Okay, so the derivative of 2 to a something is just I keep the exact same function but multiply it by natural log of whatever the base is, natural log of 2. But then I need to multiply it by the derivative of the inside function. What's my derivative of this piece? That's just, sorry, let me go back to red. That's just 15x squared. We okay with 15x squared? That's just 5 times 3. That's where the 15 comes from. Okay, so there's my derivative of my first function. What about my second function? Well, this one requires me to use this rule, right? Because I have log base something other than e. I have log base 10. So this is going to give me, but I also need to use chain rule, right? Because I have a function inside of my log function. So what is that going to give me? That's going to give me 1 over x. But in this case, because I have a function inside of it, I have 1 over 3x plus 4 times the natural log of 10, because that's my base that I'm working with for this logarithm. But now I need to multiply by the derivative of my inside function. Well, that's just linear, so my derivative is just whatever the slope is. Okay. I now have gotten all of my derivatives out of the way. So to finish this up, I just need to compile my product rule. So I'll do f times g prime. That gives me 3 times 2 to the 5x cubed minus 1 over 3x plus 4 times the natural log of 10. Now I did a little bit of simplifying there just as I went. The 3 just goes in the numerator with the 2 to the 5x cubed minus 1. Can I multiply the 3 and the 2? Can I simplify that to just 6 to the 5x cubed minus 1? No. No, because 3 is not affected by the exponent. Only the 2 is. So just keep that on the outside like that. Okay, that's my first term. Plus, now I multiply those two terms. Whew. And I get natural log of 2 times 15x squared times 2 to the 5x cubed minus 1 times log base 10. I'm not even going to worry about writing the base 10 though, because I'm good to go. Don't try and simplify that. Just leave it like that. And that's my answer. Okay. Feel free to pause the video. If you have any questions, reach out to me, or you can start trying some of the other homework problems. And then we're going to go through one more example. Okay, for this last example, we're going to talk about financial stuff again. And in the 3.3 video, I mentioned that it's important to specify what type of interest you will have, whether it's continuous interest, right, compounding continuous, or whether you're working with something like annual interest, where that interest you get every year. It's not continuously getting added to your account. You get the interest every year on a yearly basis. Well, that is going to look a little bit different. Okay. So let's say you have $47,000 in an account. Oopsies. $4,700 invested in a bank account. That earns $2.7% interest annually. So here's where it's going to be different, is you're earning this interest annually. It's not continuously happening. Okay. How would I write that as an equation? So if I want my actual amount, my principal amount is $4,700. But because this is annual interest, I'm not actually going to write it using base E, because that would represent continuous interest being compounded continuously, and annual interest works different. Instead, I can actually come up with this just by reasoning through it, what my base is going to be. If I'm earning 2.7% interest, how much will I make after the first year? Well, I can calculate that by just calculating 4,700 times 0.027. Calculating that value gives me the amount that I'm going to earn on interest for that first year, which in this case is $126.90 or $126.90. So this is the interest earned in year one. Okay, that means after 1 year, how much total do I have in my account? Well, I would just do 4,700 plus 126.9, right? Which is 4,826. So 4,826.90. So that's how much I have in my account after year one. How would I find the amount in year two? I could calculate the interest on this new amount and add it to what I currently have. Well, there's actually a shortcut way to do this. As you go from year to year, you're always going to keep the amount that's already in your bank account, plus earn that additional 2.7% interest. So you're going to keep 100% of your money plus earn 2.7% interest, or plus earn an additional 2.7% from the interest. What does that give you? That gives you 102.7%. And what does that value mean? That represents the amount that's going to be in your bank account after 1 year, or after each year. Each year, you're going to have 102.7% of what you had previously. What does that sound like? That sounds like a number to multiply by over and over and over again. So my base here is actually going to be 1.027 raised to the t power, where t, of course, is years. So if you have situations where that growth or that decay isn't a continuous growth or a continuous decay, where it's happening just like once a time period, then you can set it up in this way using percentages. If it's growth, you take whatever percentage and add it to 100%. If it's decay, you would take whatever decay rate you have and subtract it from 100%. Okay. Well, now that I have that, what if I wanted to know, how is your money changing? How fast is your account growing after a certain amount of years? Well, if I'm talking about a rate, how fast something is changing, I'm really talking about the derivative. So let's find the derivative of this function. What is a prime of t? Okay, well, according to my formula, first of all, the 4,700 just stays on the outside, and I can just focus on this piece. What's the derivative of that? Well, the derivative of that is 1.027 raised to the t, right? I keep all of that, but then I have to multiply it by the natural log of 1.027. Since 1.027 is a constant, I can go ahead and just plug that into my calculator to get a value out. And I get 4,700 times 1.027 raised to the t times approximately 0.026641. 9309. Okay. I can combine this constant with my 4,700, and that gives me, and I'll round this one, so I get 125.22 times 1.027 raised to the t. And that's my derivative. I can use this derivative to now plug in any t value I want if I want to know how fast my account is growing after 5 years. I can plug 5 in for t to get the rate at which that account is growing. Okie doke. Good luck on the rest of your homework. Let me know if you have any questions, and I'll see you in the next video.